Hi, hello. In today's lesson, we're going to study the centroids and the orthocenters of a triangle. Our goals for today's lesson are to analyze the intersections of medians and analyze the intersections of altitudes in a triangle. We're then going to identify the centroid and the orthocenter, and then we're going to use the centroid ratio theorem to solve some problems. To do that today, we're going to have a few definitions that we need to go over. We're going to go over the altitude, the centroids, the median, and the orthocenter. So our first two definitions today are the median and the altitude in a triangle. Let's start with the altitudes. An altitude of a triangle is a segment that connects a vertex to the opposite side as long as it's perpendicular. It has to create a right angle, such as this. This segment is an altitude. A median is a segment that connects a vertex or a corner of a triangle to the opposite side such that it bisects the side. It cuts the opposite side in half. So this is a median. We use the altitudes and the medians to identify the orthocenter and the centroid of a triangle. So let's start with the orthocenter. The orthocenter of a triangle is the intersection of all of the altitudes. So quick demonstration, here is the orthocenter of this triangle. Now it makes sense that the orthocenter is inside the triangle, but that isn't always the case. As long as the triangle is acute, the orthocenter is inside the triangle. However, as I move this angle A downwards, as it becomes an obtuse angle, the orthocenter moves outside the triangle. It's always going to be above the obtuse angle. Now, if the orthocenter is inside an acute triangle and outside obtuse triangle, that sweet spot in the middle, a right triangle, is going to have the orthocenter on the right angle. It will be on the triangle. There's not much else that's interesting about the orthocenter, so let's move on to the centroid. The centroid is the intersection of all of the medians in a triangle, all of the segments that connect the midpoint to the opposite vertex. The centroid is also the center of gravity. You can balance a triangle on its centroid. We also have what's called the centroid ratio theorem. The centroid ratio theorem says the distance from the vertex to the centroid is twice the distance of the side to the centroid. So in this example, the distance from the corner A to the centroid G is twice the distance of the centroid to its opposite side, GD. And we can work our way around the triangle. BG is then 2 times GE, and CG is 2 times GF. Let's use that to solve a couple of problems. Here in this first triangle, we have AD is 36, and I need to find AG and GD. So first thing to note is that AG and GD together combine to make AD. So AG plus GD equals AD. Now our centroid ratio theorem says that the longer segment, vertex to centroid AG, is twice the length of the centroid to the side, GD. So I can replace that AG with 2 times GD. Ultimately, we have 3GD is equal to 36. So the segment from the centroid to the side is 1/3 that distance, so it's 12. So if GD is 12 and AG is twice the size, that means AG is 24. Now let's check out another example where we use some algebra. Same idea, that MQ is half of KQ, or KQ is equal to 2 times QM. So what I can do is I can set up 4x equals 2 times 3x minus 4. I'll distribute the 2, gives us 4x equals 6x minus 8. If I rearrange some stuff, subtract the 4x over and add the 8, we end up with 2x is equal to 8, and then x is equal to 4. But we need to be careful that we're answering the question that was actually asked. We weren't asked what's x, we were asked QM. QM is 3 times 4 minus 4, or 8. And we'll double check that everything works. That means that KQ is 4 times 4, which is 16. And so the bigger segment is twice the size of the smaller one, which is exactly what we assumed. So we did our math right.